Alright everybody, this is our last example from section 4.8. It's Newton's law of cooling. You will be seeing this in your calculus class, and probably in Calc 2, depending on, I've taught Calc 2 at different schools. Anyways, so let's just go over the Newton's law of cooling. The temperature U of a heated object at a given time t can be modeled by the following function: ut equals t plus u naught minus t times e to the k t. and since things are cooling, k is going to be less than 0. T is the constant temperature of the surrounding medium, U naught is the initial temperature of the heated object, and K is a negative constant. So the problem that we're looking at is an object is heated to 75 degrees Celsius and then is allowed to cool in a room whose air temperature is 30 degrees Celsius. If the temperature of the object is 60 degrees after 5 minutes, when will its temperature be 50 degrees? We want to determine the time elapsed before the object is 35 degrees Celsius, and what do you notice about the temperature as time passes? So let's get started and just see what information we have, because we have our T, our U naught, and our time that we can play with. So if the object is heated to 75 degrees and then is allowed to cool, that's going to be the initial temperature, so that's going to be our U naught. And it's then allowed to cool in a room whose air temperature is 30 degrees, so that's going to be the constant temperature or the surrounding medium, so this is going to be 30 degrees. And when we read more information, we see that if the temperature of the object is 60 degrees after 5 minutes, that's going to actually allow us to find K. So this is going to be 5 minutes, and U of T is going to be 60 degrees. So when we plug all this information in, we're going to have 60 equals 30 plus 75 minus 30 times e to the k times 5. 75 minus 30 is 45, and then 60 minus 30 is going to be 30. And so we can solve for k by dividing both sides by 45. And so let's see, that's going to reduce to 2/3. 30 divided by 45 is going to reduce to 2/3. And it's going to equal e to the 5k. We'll natural log both sides. And then the 5k will come down. Natural log of e is 1. We'll have natural log of 2/3 will equal 5k times ln e, which is 1. Divide both sides by 5. K will equal natural log of 2/3 divided by 5. You might be freaking out going, oh my god, it's not negative, but natural log of 2/3 is going to be negative. So this is negative 0.08109. So then this makes our equation for this heated object to be U of T will equal 30 plus 45 times e to the negative 0.08109 109T. And the question that we want to answer, the first question that we want to answer is, when will the temperature be 50 degrees? And so we're going to replace U of T with 50 and then solve for T. So we'll start off by subtracting 30 to both sides and then dividing by 45. So 50 minus 30 is 20. 20 over 45 is going to be 4/9. So 20 over 45, divide both sides by 5, will give us 4/9 equals e to the negative 0.08109T. And we'll divide both, not divide, we're going to multiply both sides. We're going to natural log both sides. And so we'll end up with natural log of 4/9 equals natural log of e to the negative 0.08109T. And this negative 0.08109T will come down as a factor. We can divide by this K and then allow us to get T. So T will equal natural log of 4/9 divided by negative 0.08109, which is approximately 10 minutes. Okay, so I think the hardest part with this Newton's law of cooling is there's a lot more parameters that we saw than other problems, and so we just have to make sure that we take our time, if you like, listing out all the parameters, but making sure you're plugging everything in accordingly. It's also really tricky because you have you want to focus on answering the question, but before we do that, we have to solve for K first. There's like a hidden question before we can answer the question. And again, I think it's helpful to write the function out so I can just see that you've put everything together. There's a couple more questions. We want to determine the elapsed time before the object is 35 degrees. So we're going to do the same thing that we had just done and replace 50 with 35. And then what we also want to do is, what do you notice about the temperature as time passes? So let's erase all this, and I think I'm just going to create another video for the next two questions because of time. So I'll see you in another video.